So the first method of differentiation that we will go over is the chain rule, and this is with respect to composite functions. So if we have a function that is a result of the composition of two common functions or two known functions that we know the derivative of, this shows you the method of finding the derivative of that function. So let's say we had something like y is equal to g of x, g of f of x. So now I'm just gonna have a parallel example to go with this side by side, as it would just make it easier to understand why it really is difficult. Or y is equal to g of f of x. You would just think that, oh, I can take the derivative of g of f of x with respect to x, and that would be very simple. And if y was equal to x squared plus 3x plus 2, the whole raised to 4, well, you would think that you could open it up and then you would have, x raised to 8 plus something followed by a certain number of terms which are separated by addition. And so you would be able to take, and they're all powers of x, so you would be able to take the derivative. But however, this is also a much easier way, and in some cases you might not have it, you might not be able to open it up. So I'm just going to do this example in parallel to this theoretical example, and then I will show you an example of something that you cannot open up, and there is no other way to take the derivative but using the chain rule. So in this case, what the derivative, well, if you just take the derivative with respect, I mean, what most people would think you would have to do is just multiply this by 4 and minus this by 1. But if you really realize, if you really think about what you're doing, you're actually taking the derivative with respect to this entire thing, that is x squared plus 3x plus 2. And in that case, and in this case, we're writing that expression where x squared plus 3x plus 2 is just equal to f of x. Just to make things easier, if we imagine this entire thing to be f of x and the whole thing being raised to 4, because, well, g of x in this case is x raised to 4, and we think about it, then, well, the derivative of g of f of x with respect to f of x would be exactly that. It would be in this case, it would be, so the derivative of g of f of x with respect to f of x would be that. And, well, you can clearly see that that's not the right answer, because we want the derivative of this with respect to x. So we would need to still find the derivative of it with respect to x. And right now, to understand it better, we have actually just found, and right now, just for you to understand it better, we have actually just found the rate of change of this entire function with respect to a change in this. So this entire thing changes by an infinitesimal amount. We know that this would change by a certain amount, but we want to know how it would change with respect to x, which is why we would want the derivative of this to be with respect to x. And, well, we can try and find the derivative of f of x with respect to x, which would be the derivative of this, essentially, which would be 2x plus 3. And, well, if you think about it, by multiplying these two values, I should get the rate of change of the derivative, the rate of change with respect to x. So if I multiply the rate of change of g of f of x with respect to f of x to the rate of change of f of x with respect to x, it is telling you how much g of f of x would change with respect to x. So I didn't mean to confuse you in any way, but basically what it says, if I change x a small amount, then f of x changes by a resulting amount, which relates to it by 2x plus 3. And if f of x changes by a small amount, then g of f of x changes by a resulting amount, which is this. And so if x changes, then we would need to multiply this that many number of times, and that does make intuitive sense because we're dealing with a really small change of this, but in reality that is because of the small change. So, and if you think about it algebraically, this should technically cancel out with each other because they should be equal, but we can't actually cancel them out. So we could write it as the change in g of f of x with respect to f of x being multiplied by d f of x with respect to x, which would be equal to 4x squared, which is equal to that. So this is what dy by dx should be. And I hope that made sense, and I hope you understood the reason why that happens. To find the instantaneous rate of change of this thing, we find the change that x causes on f of x, and multiply that by a small change in f of x causing that on g of x. And so now to solve a more complicated question, as I had spoken about earlier, we could look at something like sine of x squared plus 4x. Now this is something that you cannot find the derivative of by opening anything out. So again, we want to find dy by dx, which can be written as d of y, which is in reality, or d of y, which is in reality sine x squared plus 4 with respect to the change in x squared plus 4x times the change of x squared plus 4x with respect to the change in x. And that should make sense because again we want to see what a small change in x would cause to x squared plus 4x, and then a small change in x squared plus 4x resulting in the change in sine x, and then multiplying the two to find the overall change, or how the overall small change of x affects sine x squared plus 4x. So we know that the derivative of sine x is usually cos x. So of sine x squared plus 4x with respect to x squared plus 4x should be cos, and then the derivative of x squared plus 4x with respect to x, which would be 2x plus 4. And that's how you use the chain rule. So the proof of the chain rule is actually pretty simple. So if we assume that h of x is equal to g of f of x, then the definition of h of x, using the limit definition of a derivative, would be as x tends to a particular x value, that is x sub 0, which I'm going to be calling x0 from now on, as g of f of x f so as this, which is the slope of it, as x tends to x0. Now this can also be written as the limit as x tends to x0 as g of f of x. So this can also be written as this, and as you can see, what all I've done is I've multiplied this by f of x minus f of x0 in the denominator and the numerator. And this actually just doesn't change the function at all because these can be cancelled out. We're just not cancelling them out. And it can be written in this form. And if you notice that if we just look at this, this is the derivative, this is the definition of the derivative of g of f of x with respect to f of x. And then this, as x tends to x0, is a definition of the derivative of f of x with respect to x. So that is why we can say that h dash of x is equal to g of f of x d, the change of g of f of x with respect to f of x times the change in f of x with respect to the change in x.